Good morning, it is Anagon Live and this is day 14 of Advent of Code. I am very late today but still on time, and day 14 is going to be released in just a few seconds. Let's have a look and enjoy. Day 14. Space Stoichiometry. As you approach the rings of Saturn, your ship's low fuel indicator turns on. There isn't any fuel here, but the rings have plenty of raw material. Perhaps your ship's interstellar refinery union brand Nanofactory can turn these raw materials into fuel. You ask the Nanofactory to produce a list of the reactions it can perform that are relevant to this process, your puzzle input. Every reaction turns some quantities of specific input chemicals into some quantity of an output chemical. So it seems like we're going to have to simulate chemical reactions. Almost every chemical is produced by exactly one reaction. The only exception, ore, is the raw material input to the entire process and is not produced by a reaction. You just need to know how much ore you'll need to collect before you can produce 1 unit of fuel. It looks a little bit similar to the dependencies that we had earlier with the orbits. Each reaction gives specific quantities for its input and output. Reactions cannot be partially run, so only whole integer multiples of these quantities can be used. It's okay to have leftover chemicals when you're done. For example, the reaction 1A, 2B, 3C results in 2D, means that exactly 2 units of chemical D can be produced by consuming exactly 1A, 2B, and 3C. You can run the full reaction as many times as necessary. For example, you could produce 10D by consuming 5A, 10B, and 15C. Suppose your Nanofactory produces the following list of reactions. Okay. Different reactions that are possible. The first 2 reactions use only ore as inputs. They indicate that you can produce as much of chemical A as you want. Okay, right, but you can also produce B, each in increments of 10 units, each costing 10 costing 10 ore, and as much of chemical B as you want, each costing 1 ore. To produce 1 fuel, a total of 31 ore is required. Okay, 1 ore to produce 1B, then 30 more ore to produce the 7 plus 7 plus 7 plus 7, 28A. Let's see how that looks. Yeah, okay. With 2 extra A's wasted, required in the reactions to convert B into C. Okay, and so on and so on. Or suppose you have the following, okay. Then what is our goal? Given the list of reactions in your puzzle input, what is the minimum amount of ore required to produce exactly 1 fuel? Okay, so I think right now about a search algorithm that is going to try different ways to produce fuel, like some kind of A-star algorithm. I'm not sure exactly how we're going to solve this puzzle. It seems to be quite a complicated one for now. But I'm sure with a little bit of help we'll get there. So of course we'll start by just processing the input at least, and then we start by conceptualizing like what we're really doing and how we can reach the goal state of producing a fuel. It should also be clear by now that just trying every possible combination might not be possible, because there are a lot of different chains and you could do it in so many different ways that it's not so clear. Okay, let's go over the input first. We do an open on day 14 input, and we read all the lines there, and then we are going to transform every line. And how we transform it is by stripping first of all the white space, and then we're going to split it by something. Or maybe I'm actually going to use regexes today, because I haven't used them yet. And they might come in handy. I'm not entirely sure, maybe not. I think I'm still going to split by this arrow sign. So now we have those left and right hand sides. And I want to kind of, let's see, we then need to split the right hand side again and the left hand side also. So maybe it is a little bit easier to do it in a loop. Let's see if we can convert it into a loop automatically, but no, we cannot. So we do it like this. So this is the equation, kind of. And then on the left hand side of the equation, left hand and right hand, there we can, let's see, we can split by comma. And all the commas are succeeded by a space. So the left hand elements, left hand ingredients, and the right hand ingredient is just the digit with a single chemical. So right hand count and right hand chemical, or maybe element. That is going to be the right hand and splitting by space. And right hand count, are we going to parse it into an integer? I think we do. So that is going to be an int. And on the left hand we have to do the same thing. So I'll make a little function that will parse something into an integer and an ingredient. It looks like this. Parse ingredient. Nothing happened, so I have to make it by hand. And that is the string. So we're splitting the string, and then we have an element and a count, and the count will be replaced, and then we return the count and the element. And so for the right hand count and the right hand element, we have parse ingredient with the string, so that's the right hand, and then we're going to do the same on the left side. So the left hand ingredients is going to be, we're going to iterate over all of the ingredients. So for ingredient in left hand ingredients, and then we're going to pass that into parse ingredients like this. And then what we need, let's see, now we are going to have to think about how we're solving the puzzle, in fact, because I have no idea yet. I am printing everything to see that what we're doing seems to make sense. Right hand ingredient, and we need to run it like this. So we are parsing correctly already. That's a good start, and I think I'm gonna step away from calling it right hand and left hand, but calling it instead input and output. Alright, so that's the parsing. That is not so hard. But now about what we're actually doing. And I will start with an example so that we understand at least the simplest case. So in the example we have 10 ore that produces 10A, and from A we can produce a bunch of other things. We can produce either, let's see, we can produce either, if we have an A we also need a B. So it's kind of like this. So ore can produce A, and it can also produce B, and that is in the ratio of 10 to 10. and for B it's in the ratio of 1 to 1. And A can then produce, together with B, a C. And to do that we need 7A and 1B, and we'll produce 1C. And 1A and 1C together can also produce 1D. Ah, okay. So that means A is going to be reused a couple of times. It reminds me a little bit of Factorio, by the way. If you've played Factorio, you will see that this is very similar. Unfortunately, I never spent time in Factorio to actually do these kinds of calculations, so it's something I'm not trained in. So 7 A's combined with 1 C will produce 1 D, and 7 A's with 1 D will produce an E, and then finally 7 A's with 1 E will produce, and this is a little bit tricky to draw in fact, and that one will produce 1 fuel. Okay, now let's see how we can actually solve this. It seems at first already that we need to start with the end, that we need to start with fuel and see what we need for that, and every time go a step back and see what we need for that, rather than starting with the ore and then seeing what we might be able to produce from the ore. That's the way I think I'm going to try it today. Okay, so let's say that we start with the ore, and then we know we need 1 E and we need 7 A's, and oh, excuse me, the whiteboard was off. So to get 1 E, then we need to have 1 D and so on. So I think we can just go over the list in reverse and then produce the correct answer. But now there's the thing that we might be able to... Oh, it says that every output chemical is produced by exactly one reaction. Almost every chemical. The only exception is ore. That is not produced by anything. Okay. And we'll have as much of it as we need, I think. Okay. So we're going to start by fuel, and we need to keep a list of all of the reactions. And the reactions is basically a dictionary. That's how I'm going to do it. A default dict. No, maybe not. Maybe just a normal dictionary. And what we're going to store in there is for every chemical that we're trying to produce, how much you'll produce of it and what ingredients you need. So we're storing actually the output ingredient. And the output ingredient will contain the element and the count, like this, and I am storing only the element, and or rather I'm using the element as the index, and then I want to keep in there let's see, I want to keep in there a few items, namely the output count and the input ingredients. And I find it a little bit weird to have count first all the time, but I'm going to stick with the example. And at the end we can print our reactions and see that it looks the way we're expecting. So here you see for every element we know how many we are producing and what we need. So let's start with target. Target equals fuel. And then let's see what we need. Needed. That starts with an empty list, and then we're going to do an infinite loop. I'm not sure when we'll stop exactly, but I guess when needed is empty, that's when we'll stop. So while needed, and that means that we can actually do it like this. So we need at the first one fuel, like this. And then let's see what we need for one fuel. So the reactions for fuel, let's see, the element count and element equals needed. Let's say that we pop the first item, so we know how much we need and which we need. So what we need for the element named fuel, that is going to be returned by our reactions, and that is output count and input ingredients, like this. So that means that we need to multiply by output count, I guess. Let's see how that looks. So for actually I was a little bit in front of the screen, I'm sorry. So if we have one fuel that we're producing, but for that we need, let's say, 2 A's. Hold on a second. Let's say we're producing 2 fuels from some kind of reaction, and for that we need only, well, let's say we need 3 A's for that. That means that if we are looking to create 1 or 3 fuels, so let's say we need 3, then we're going to have to produce more than 3. And if it was 4, of course we could just run the reaction twice, but if we need 3, we also have to do it twice. So we need to find the first multiple that is higher than what we need. So I'm going to be a little bit more explicit. Needed count and the output count like this. Needed element. So let's say that we need we need 3 and output count is 2. Then how many times we run the reactions? That's basically how do we do that? I think what we can do is that we divide the needed by the output, and then we round it up, so that means sealing. So the reaction count is like this, actually. And we can use math.seal to import. And the needed count is what we're using. So now we know exactly how many reactions we have to run this for. And that means that the input counts that we're getting, so for each ingredient, how many we need of those, are going to be multiplied by the reaction count as well. So let's go over the input ingredients. And we can actually explode it, input count, input element. And input count is going to be multiplied by the reaction count. Like this. And then we're going to add that to the needed list. Needed.append. And what we need is the input count and also the input element. And then basically that's it. Then we're going to loop until we're done. And then what do we get in the end? We get a number of ores that we need, and that's a reaction we cannot actually solve. So the ores that we need is, I guess, the output for the question. So actually when needed contains only ores, that's when we're stopping. And let's see if we can actually make a little filter here that counts only the ores. So n for n in needed, and if n, actually we should explode it. So the count and the element, and if the element equals ore, then we are looking at only the ores. Let's see how we can actually solve this. we need to count the number of ores. No, we need to count the number of things that are not ores. And as long as we have some ores left, something other than ores in our needed list, we're not done yet. So let's say we are just summing every element, or let's say len. It doesn't matter what we're outputting here actually. We could do the elements, and as long as something is in this list, okay, so that means we don't need a length, we can just use the list itself as the condition. So as long as we have something that's not an OR, we're going to keep this loop, and we're going to print the needed in the end. And we have a bit of a problem with a key error called OR, because there is no OR in our reactions, and that is correct. So if we are looking for OR, then we're going to continue, because that's not something we can look up. So needed L. If it's not in the reactions, then we're going to break, basically. And here's what we get. We are breaking, but we still have a lot of items there. So that means we should continue, we should not break. And now we have a whole bunch of ores listed in there. So let's sum it up. Let's print the sum of all of those counts. For count an element in reactions, no, in needed. That should be the answer. Okay. That's not the right answer though. Okay. We do have... It looks kind of correct. Let's see. Okay. I'm going to run in debug mode and see what happens. Let's also see if I read the instruction correctly. Given the list of reactions, what is the minimum amount of ore required to produce exactly one fuel? So we need to produce one fuel and no more. Okay. So I see that no one has solved it yet, so it means that probably it's not as simple as I think, or I'm just doing quite alright, but of course I haven't reached the answer yet. But I feel like I'm quite close, I'm doing quite well today. So, let's see, we're stopping at the right position anyway. And why do we keep waiting there? Okay. So I'll put the breakpoint here. So what we're needing right now, I need to remove all those old variables. The needed element for now is fuel, okay, and the output count for the reaction that we're getting is in reactions. So we have the input ingredients. It kind of is bothering me that it's not showing the values here on the screen. Normally it does that, but it doesn't do it all the time. Not for output count, for example. So these are the input ingredients. We need a whole bunch of stuff. And let's see. Of course, what we could also do is just, instead of increasing the input count... Oh, I didn't realize something. Something that I didn't realize is that we are going to get multiple... We are going to get outputs from those reactions, so we can actually... we have leftover ingredients that we can reuse, so we might not need to run some of the reactions. Let's see how we can actually solve that. So I forgot that every reaction creates outputs, and not only the outputs that we need, but maybe some more. So we also have available, and that is going to be a list of, no, a dictionary of chemicals with their counts. And for that I'm going to use a default dict, so that we have 0 by default. import it. So after we run the reaction, let's see. So first we have the needed elements, but we can first see if we already have them available. So let's see, the available element is available for this particular output element. And then basically what we are using is what is available. No, it's what is needed. Let's say we need 3 and we have 2. That means we're going to use 2, right? So we're using the minimum out of the out of what we have available and what we need. Needed count. And after we use it, we're going to make what was available 0 for that particular element. And then also what we have left afterwards. What we have left afterwards is of course the available minus what we are using. And now we know what is left and how much we're using, and then what is still needed afterwards. It can be, of course, that we still need 1 in the end. So I'm going to keep a needed count, what is kind of left over. I'll call it still needed count, is what is needed minus what is available. Let's see how that works. I guess what is still needed is how much we are able to use. Yeah, what was needed, and then minus what we're going to use. So if we still need ingredients, then we're going to have to loop. Actually, I'm not sure if what I'm doing is correct. So I was looking up the available. Hey Starkey Blood, good morning. Have you already solved part 1 and part 2, or are you just watching? I think I'm making a small mistake here. The available ingredients that we're going to use, that's not what we're going to use for the output elements. You've not long woke up, my friend. So you just woke up. Cool. Just watching. Okay, so actually we need to look what we have available for the input ingredients and not for the output ingredients. So that looks like this. So we need several inputs for a certain element, and that is the input count. And I'm going to call this one needed input count. I'm going to be very explicit with my variable names today because I feel that there's so much options for confusion. So the needed input count, that we can check with what we have available. And available count, actually, that is what we need. Available count. And that's what we are using, and still what we need after that is how much we're using minus how much we're needing minus how much we're using. No, that's not correct. What we need is total what we need minus what we're already using. Okay, and then only if we still need more of this particular element, then we're going to actually apply the reaction. So not all the time. And oh yeah, and of course after we have used something, then we're going to update our available counts, and we're updating the input element at this moment. And then if we still need some more, then we're going to run a reaction, and it looks like this. The still needed count is what we're looking at. At least once the needed input count is going to be multiplied, but I want to do that in line. So I'll do it like this. And that is then what we need. I think now we can safely run it. Let's see. No attribute default dict. Default dictionary. No. Default dict without an underscore. I see. Now we get a number and let's see if it is correct. It's not right. And unfortunately I didn't save my previous attempt. So I'm not sure if it is actually different from before. I guess this was what I had before. And it looks like it was the same. So that means that nothing actually changed. So let's see how that is possible. I am checking here if something is in a dictionary, and I want to make sure that it's actually checking the keys and not the values. But I think people have pointed out to me yesterday that it is looking in the keys and not the values. So here we have this part. Let's see what it says. Not in reactions. Oh, and the needed element is fuel. Well, that is correct. Is it correct? We need fuel and it says it's not in the reactions. How is that possible? The reactions array looks like this. And it should contain fuel, doesn't it? Shouldn't it? I don't see it here. Okay. But how are we able to run so many iterations if it doesn't exist? So running again, looking at our reactions, and it should contain fuel, right? Oh yeah, I see fuel here. But at this point, we don't find it, and not so clear why. We have a needed element and it's not. Okay, and it says it's not in reactions. I think that maybe there is something wrong with my check. So fuel, I think it should be there. It says true now. Okay, let's just run it and see. So here we have fuel and oh, I'm doing a not in. Yeah, okay, of course. When I say not in, it's false. And that doesn't trigger the condition. And so it will continue. And the needed input count is 1. And let's see. So we're actually now looping over all the needed ingredients and we have 0 available. And we needed 7 of ZKM. And we are going to use 0 of what is available. And then we still need 55. Is that correct? It doesn't sound correct. And the current reaction that we're doing is, you can see it from input ingredients. It means we need 7 of ZK and 1 PV. And here now it says we need 55. That doesn't seem to be correct. And still needed count was the needed count that is written here says 55. But how did we end up having 55 there? We are already in the second iteration. That's what it looks like right now. The needed element is not fuel anymore. So that means I skipped somewhere, not realizing it. So we were doing fuel and we have some input ingredients, namely MB, and it says we need 55 of those. Let's look at the input. Yeah, we need a lot of inputs for this first reaction actually. So we need 55 and we have not anything available. And so what we're using is 0 and then we still need 1 afterwards. That sounds very but not correct. So the needed input count, that's actually what we're going to use. And then what is needed count? that's the needed output, right? And we're looking at the input right now. So I should have used needed input count instead. And let's run the whole reaction again. Now we get something different. I'm going to post it right now. And it's also not correct. So let's carefully look at what is going on. So our first reaction. Hey Emily, good morning. Have you already solved it? I see. Okay, so you're doing quite well. No, you're just online. I'm sorry, misread the leaderboard status. Just to make sure that the stars are working today, I'm going to do a little demo of the stars. There we go. Where is it? So if it works right now, a star should come up. If it doesn't, then today's stars are not gonna be working. And apparently Hans has already solved the puzzle and the stars are not showing up. So very sorry, Hans, but congratulations on solving both parts. And Emmy Flake, you're working on it. Good luck. Don't be too much distracted by my babbling. When you are finished, do come back online, of course, and let's have a chat. It's a fun puzzle so far. It's not too complicated and you can really analyze it step by step. So we need 55 MBs and we have 0 available. We're going to use 0 then, and then what we still need is 55. And then we're going to say that the new value of what is available is going to be 0 still. And if we still need any of that input, then we're going to run a reaction. And we have, let's see, 55 needed. And the output count of the reaction is... Oh, what is the output count of this particular reaction? Wait a second. I think I'm mixing up 2 reactions here. The output count is the output count of the fuel in this case. And the needed count for the fuel and how much we have, that is... Oh, I think I did actually do it correctly earlier on. I did do it correctly earlier on where I was looking at how much fuel we need. Right? Yeah. So if we need to have 1 fuel and we have a reaction that requires 20 other chemicals, we can just append the 20 other chemicals to the list of needed elements, and then if we have them available, we take them from the available one, and otherwise we'll run a reaction. So we don't need to look at the dependencies of the reaction. It is really about this part. So I just made a little bit of a thinking error there. So it's about the output count. That is what we're going to check. So we have available what the needed element. Let's see how much we have available of the needed element. And if we have anything available, we're going to use it. And the needed element count minus the using count is what we still need after that. And what remains is what we are using minus what we're having available minus what we're using. And if we still need any input or any of this output element, then we're going to run the reaction. And we're going to look at every element that is needed for that reaction, and then we'll just append it to the needed list. And our next iteration, when it's going to handle those needed elements, that is actually going to make sure that we're reusing available elements. And the reaction count is how much we need versus how much we get out of that reaction. So that is the same for every input element. And then we can just append the needed input count for that reaction multiplied by the number of reactions. and that is an appended. That is appended, and that means also that there is a chance that we're actually we are actually having multiple needed items. So let's say we add twice a dependency to the same list. So I think a list might not be the greatest data structure for this case. We get again some output that we had already before. And I'm not sure if it would be related to what I just pointed out. I guess it might, because we get a lot of leftover chemicals that we... Yeah, okay. So I'm not entirely sure, but it feels a little bit more precise to use a dictionary for the needed list, like this. So what we need first is fuel, and we need one of that. And now we can actually look at all the needed. Let's see how we are going to count. How we're going to count how many non-ores are left in this dictionary. So we need to break at some point, and we need to break when all we needed is ores. So maybe we can do like items. So where the element is on the key part of the on the dictionary item, and the count is on the right. So then basically our condition is still correct, it's still the same, and except that if we're appending, we're going to increment, and maybe we can use a default dictionary for that instead of a normal dictionary. And that means the needed count is 0 by default, and then needed fuel is going to be 1. Hey Alex, you screwed up today. You understood the problem incorrectly. You didn't know it was allowed to leftovers. Oh, I'm sorry, man. And now you haven't finished it yet, and you're going to be not on the leaderboard. Very sorry to hear that, but you still have a lot of days left, and you did so much. You did so well so far. Oh, you need to restart. Oh yeah. Hey Hans, I saw that you solved it, the first one today. Good job. Did you find it very easy to do? So the needed input element, let's see, we call it input element. That one is going to be incremented with the value here on the right. Maybe that is going to solve the problem. Let's see if we get a different output at least. We do get a key error right here. So we're popping. That is something that we cannot do. We need to actually... is there a certain order in which we need to iterate over all those items? I'm not sure. How do we pop in a needed list? That is a little bit of a problem. I think that I might need needed elements. I might need a list that I can pop from. So just append, or maybe it can be a set, and we can add to the set. But I don't want to add or ever in the needed elements, because you cannot generate or. So if the input element is not or, then we're going to add it. And if it is or, then we're actually just going to count it. That is another way to do it. Then our while loop is going to be so much easier. Then we just need to check if needed has data in it. So if we don't have or, then we're going to add the input element like this. And otherwise we're going to increment the needed or. You tried to do it in Prolog. Wow. You say it's quite easy actually. Okay, cool. Well, let's have a look at your Prolog code if you manage to, in the end, solve it in Prolog. So now we have the needed ore like this, but something is not going right. We are extracting from needed, but we need to pop. The needed element is from the needed elements, just popping the first one, and or actually it's a set, so we cannot pop any particular item, and then we can use that one to figure out how much we need of it. I think that should be correct now. And we're popping from an empty set, and that is because we didn't add the fuel to the needed elements. Like this. And now we're trying to actually do something that is not correct, because needed with an input element is a set, and now we're trying to hold on, what was the output? Unsupported operand types int and tuple. So here's the tuple. We don't need that anymore. Just do it like this, and we're popping from an empty set still. So I'm not sure. I guess we're going to do it like this. Oh, now everything is breaking basically, and G says it's pretty hard. Okay, I guess for some people some problems are harder than others. Okay, I'm going to do debug mode and see what happens. So the needed element is fuel, and it says we need one of those, and if the needed element is not in reaction, so we're skipping. Then let's say we found the reaction and we know how much output it results in, and it's not showing it on the screen, but we need one. We retrieve one from this reaction, and what we need from that is a whole bunch of things. And we have nothing available, we're using nothing, and what we still need after that is one fuel. And so after that, what we need, let's see, what we have available is still going to be 1, of course, 0 I mean. And then if we need more than 0 of the output chemical, then we're going to run reactions. And you'll be back after you finish it, that's fine. Please do work on your puzzles if you want to be on the board or you want to get a good score. So good luck, and see you just right after. The reaction count is 1. And by the way, I am going to change my stream format a little bit. I'm going to work until the end of the first hour, and after that discuss solutions if people have solutions. And if they don't, then I'll just keep going until 1.5 hours into the stream. I'm going to limit my stream time from now on a little bit. I feel like the other aspects in my life are suffering a little bit from the excessive streaming, let's call it that way. Well, it's not excessive really, but we all need to balance what we do in our lives and how we divide our time. So we have 55 that we need, and the element is MB. And here we've decided that we need how much? 55 of that element, and we're adding it. And do we actually decrease needed after we're doing a reaction? I think we're not. So after we run the reaction, we actually do have to decrease the needed element. Well, we popped it already, so that's correct, but needed count should really also be reset. So let's assume that after running all the reactions, the needed element is going to be 0. Right? That makes sense. And then let's run it again and see if we get a different output. But we get some bugs. So let's keep going. Might it be that we do get ore appended to the needed elements? Maybe. Yeah, so that can happen, of course. Let's do it again. Still too many values to unpack. Where does it happen? It happens here. It just happens in counting what we need. Okay. So needed was a dictionary, and it should contain only fuel, but I'm not sure about that. Needed.keys. Let's see if we can do that. L for L in needed.items, and we have a count here if C is bigger than 0. So we need nothing, and the output of what we need is actually different. It's the needed ore. So we get 31 ore. That sounds very low, but who knows, maybe it's correct. No, it's not correct. No. Okay. I've already tried a very many answers. 31 is the answer to one of the examples. That is weird, but I'm not using the examples as my input. Okay, that's true. I can use the examples, of course, to figure out if I'm doing it right. Hi, Aneurysm, by the way. Good morning or good evening. Okay, so let's go over this again. Hi. I see that my music has stopped, unfortunately. So I'm not entirely sure why. But I've had a lot of problems with music. Twitch has muted my audio, and then this morning I tried to play YouTube, and for that I wanted to add a filter to the sound because most of the sound was coming from the left, and I wanted to make it mono. But then I crashed my input source, and now I cannot use that anymore just before the stream, so sorry, that's why we have no chill out music today. And my alternative solution just crashed apparently. So it's just quietness and me talking. If the input element is not ore, we're going to add it to the list, and we are dealing with input element right now. The MB, yeah. We're going to see how much we need of that. It's 55, and the reaction count is 1. So we're going to need 55 of those. Okay, and we're going to run that loop several times, of course, like this. So that is another one. Needed element here. Input element. Where are you? That's this one. We have another one, another one, another one. The last one is going to be PB. So we run it till we get PB. It's this one. And then we are now already out of the inner loop. And it says we need PB. Okay, so we're popping from the last element. I think I want to do a depth first search, so we're popping from the first element instead of the last one. And it says pop takes no arguments. Okay. And we do have a set, right? We do have a set, and that's why we cannot pop the first one. Maybe we can just use a list instead and append, but I don't want to append if it's already in there. So maybe we can just make this list unique afterwards. Needed elements is... This is a little bit of a hack what I'm going to do now. Very much of a hack. I'm going to make a list out of a set of the needed elements, just to make it unique again. Okay, and add is not a method on a list. And why do we get a highlight over here? I'm not sure why. So let's run it to the second loop, and now it says that we need ZT. That is it's not the first one from the list of things. MB should be the first one. So I'm not sure why we are running into ZT first. It was number 6 actually. Maybe because we made a set out of it and then we made it into a list again. So instead of this, I'm going to check if the element is already in the list. If not in needed elements, then we're going to add it, and otherwise not. So we should start with MB. That is now working. Then let's look at the second one. Apparently we need 55 of that as well. And let's look at our input if we can recognize that in the reaction list. Yes, it says we need 55 of KH, but that is not really correct. But after we actually unpack that value, we do get 61, which is the correct value. And to get 61 of KH, what we need to do is to run a few reactions like this one. So let's see if we need 61 of those and we can get 8 per reaction. That means we need to run at least 8 reactions. Let's see if we get that correctly calculated. So if we need more than 0, yeah, and we do, and the reaction count is calculated to be 8, so that's also correct. And then to do 8 reactions we need, let's see, 8 times 11, 88 of the GD thingy. And what do we calculate? In fact, it says 11, but the actual needed input count is going to be 88. That is indeed correct. And we're going to keep track of that. And only if it's not in the elements, we're going to add it to the list of needed items. So there we did it. And then we're going on with the next one. And we also need... Oh, are we looping over it twice? We're now looking at KH. Oh, that's a different... Oh, that's the same reaction still. Okay, the loop was actually done. It was just evaluating whether it was finished or not. And then we're going to go over again the lists, and we now need KH. No, we haven't unpacked yet. Now we need DS. So, okay, it seems like the reactions are running kind of correctly. That's how it seems so far. And here we have ore that we need. Maybe what we can do instead is just to add everything. Oh, I'm adding 1 to the needed ore. That is of course very incorrect. The needed input count. Yeah, okay, I see. So I was just adding 1 for every ore, but that's incorrect. Now I'm pretty confident that this is going to be the right answer. No, but it's not. So still something is going wrong. Needed input count. That is the input for the current reaction. And so let's say we need ore. Ah, yeah, we have to multiply it by the reaction count. Just like that. And if I would have just multiplied it right away, then we wouldn't have made that mistake. So I'm going to overwrite the needed input count. Like this. And we run it, and then we get a very, very big number. And let's see if that is correct, but I think now we're going to have to wait. We're going to be too early because I tried already so many times. And I need to wait 4 minutes, and that sucks. That sucks a lot. And I don't know what the second part is, so I can't really prepare. But instead I'm going to run a little example and see if the example gives me the correct outcome. So that is going to be a new Python file called example1. No, not a Python file, excuse me. It's going to be a text file. And we cannot make a plain text file, but we can make a file. Example1.txt. And let's run it there. See what we get. We get 42 as an answer. And it says that it requires... Wait. The example that they give here doesn't tell us how much ore we need. So I'm going to use another example. And that one says that we need 166. That is also not correct. It says it requires 165. Okay. Consume 45 ore to produce 10A. Or let's look at the fuel first. We're consuming 2 AB, 3 BC, and 4 Ca to produce 1 fuel. Okay. So that we are also going to create 2 ABs, and that's done here. Okay. I'm going to say, let's see what we do. We are running a reaction, and let's print that we're running the reaction. So we're running the reaction with the inputs that we need. That returns the output, a single output, and input ingredients is the argument. And then we have an output element, and the output count that we're going to get, that is also important. So after we run the reaction, of course the available counts are going to go up, right? We might have some leftovers, and I didn't actually save it. Yeah, I didn't actually update my available count. So here I reduce available by the number of elements that we're using, but after we're running the reaction, of course the available ingredients are going to be changed as well. They're going to be changed for let's see, how does that really work? So let's say we have, of A we have 3 available, and of B we have 2 available. We're going to run the reaction X, Y results in 10A. We need to do that for some reason. Then we're going to increment A by 10, right? And then we're going to see how much we need for X and Y, but that's just appended to the list of ingredients that we need. So we're going to change those availabilities in the next iteration. So what is available of the output element, of the needed element, that is going to change. It is going to, let's see what. So we need 0 after the reaction, but we might still have something left afterwards. Is that possible? Let's see, say we need exactly 21 of something, but the reaction produces 20, then we're going to have 19 extra. So the reaction count is like this, and production count. You're exhausted tonight, so you're heading to bed early. Good luck, good night and good morning. Sure, have a good sleep, Hans. Thanks for joining. It was nice to have you on the stream so many times. So the production count is going to be the reaction count times the output count, and the remainder count left over production count is the production count minus the needed count. Still needed count. Man, this is a lot of arithmetic. I think I might be doing it in a little bit of a complicated way, but so far it seems that I need to have all these components of the calculation. So the leftover production count is what is going to be available after the reaction. So available for the needed element is actually what is left over, and that is going to be added actually. Right, and the still needed count, that's correct. Okay. Yeah, okay, so there are cases where our reaction underproduces and where it overproduces, so that's why we have the two different steps where we calculate the availability after taking what was already available, and then what we are going to overproduce for those cases where we have too much. Now we get 100. Let's see what we get. We still get 166. And let's look at the overproduction right here. If we're ever getting an overproduction, I want to stop when we have some overproduction. So let's keep running all the time. And now it seems like we do. We have an overproduction of 1 because we had an element called B that we needed to produce. And we need 23 of those. But the availability was 0. So we're not using any, and so we still need 23, and that means that afterwards availability is going to be still the same. But if we need a certain element because we need to run another reaction, okay, yeah, that means we can keep it in availability. Hey Arcanian Archer, good morning. Let's see, you've already solved part 1 and part 2. That's very good. Is part 2 very difficult? Because I am not going to have a lot of time today to solve it. I'm going to end the stream today at 7:30 a.m. in 25 minutes. So let's see, where are we? And sorry, today the music is not working. I have technical difficulties and I didn't have time to fix it. It's easier than part 1, okay. So the leftover production in this case is 1. And so that means that the available elements of the one that we need, B, is going to be 1. So that will be interesting to see if we're going to need B later again. And then let's see, we have an input ingredient that we need, and that one looks like, let's see what we need. Input ingredients looks like a list, and it just requires ore. That's all it needs. Okay, so when we are going to go over the ore, it says we need to do how many reactions? Needed input count is 64. Is that correct? Our production count is 24, and we need 23. Okay, we need 23, and our reaction count is 8, and we have 3 per reaction, so that is indeed correct. We will have 1 output left, and that means, okay, where are we right now? We are right now here at this line, and the input element that we need is ore, and we need 64 of it. And so if we are not dealing with ore, we're going to go to the second part, and here we just count the number of ores that we need and add it. And then we have another element. It says we need ore again, or maybe it is going to end the loop. Yes, it is. And we say that the element that we needed, which was B, is now going to be 0. And technically you might say that it's -1 because we have 1 extra. Is that actually needed? Let's say we need another 1B later. We still have it available, so I guess we don't need to make it -1. As you can see, we still have 1 left. Okay, any hints? If anyone is seeing where I'm going wrong, please let me know. I want to get part 1 solved in the next few minutes, and I'm pretty much there, I think. And oh yeah, actually I had a solution and I wanted to try it, but I was not allowed to actually submit it. But now I noticed that my example was not correct. At least I think it wasn't correct. I'm actually 1 off. Oh, hold on a second. I actually lost a little bit track of what I'm doing. So I'm 1 off for the needed ore. How is that possible? So we're... okay. Maybe it's because we have 1 ore available already or something? No, that's not how it works. The needed element is here and we're going to add it to the availability. Let's see if we have something available also. Available. So if we have 1 ore available, then that means that no, we don't put ore in the available lists. So how can I have 1 extra ore needed? So we need... so let's look at every reaction and say how many ores we need for that. And that is going to be decided here. So we're going to print every time we need ore. That is actually on this part. The needed ore for this case is the needed input count. And needed for the element. For element X, we need so much ore. And the element we're looking at right now is needed element. Like this. Okay, let's run it and see what we get. So for A we need 45 ore, that's correct. For B we need 64 ore. For C we need 56. And that is all correct. And let's look at... let's print it for all cases. So not only for the ore, or we're just going to print every reaction. Okay, I'm trying to actually move my line up, and sometimes it seems to not work. So here we need some specific input element and a specific count. So for AB we need 6 input element, hold on, we need another variable like this. Okay, so for fuel we need 2AB, 3BC, and 4CA, that's what's written here. Then we need for AB 6 A's, and we need 8 B's, that's also correct. And let me actually just pop out. I'll just keep focused on the left side. And what it says here is that for BC, that's this one, we need 15B and 21C, that's correct. For CA, we need 16 C's and 4 A's, that's also correct. And for C, we need 56 ores, 64 B's and 45 A's, that's all correct. So the total number of ores that we need should really be 165, right? 45 plus 64 plus 56. Yeah. So why do we actually count one too many? It's a bit strange. Do we break on time? Let's look at all the reactions that we have and what is needed. The needed ore is counted. Maybe... yeah, I'm not so sure how it works. So I'll give myself 1 more minute to actually solve it, and then we'll look at some of your solutions for both part 1 and part 2. So if you have a solution that you want to share, please do paste it on Pastebin, Pasteboard, GitHub, or somewhere else, or Gist, and then we'll have a look at it. So what I'm printing here is what is available. and trying to show the terminal like this. Let's make sure it stays open. Maybe what I can do is actually append OR to the needed elements list. I think I don't want to do that. So maybe what I can do is to keep track of every time I'm adding and see when I'm adding and if that is really correct. Or like this. Oh, needed OR starts with, oh no, I'm starting with 1. That is crazy. Oh my god. Okay, so actually, I think I got it right. Let's run it. This is the answer, right? Yeah, okay. Wow. Okay, that was very annoying actually. But we did solve it, and I think, yeah, the code is quite okay. It's following every step just very precisely. Thanks for the cheers, Aneurysm. This is the good one. For part 2, I'm just going to read what part 2 is about. After collecting ore for a while, you check cargo hold 1 trillion units of ore. With that much ore, given the examples above, what is the maximum amount of fuel you can produce? So basically that means that we're going to start with an availability for the ore of that amount. Like this. So do please post your answers and your solutions. If no one would post anything, I'll just try to solve part 2 within the remaining time. How much can you produce? What is the maximum amount of fuel you can produce? So basically, let's say that we are going to add ore to the needed elements instead of not doing that. But you know what, I'm actually going to commit first, because otherwise I'm going to forget how I solved part 1. So this file I'm going to commit. That is day 14, part 1. And that will be restored. And so if we do have ore, we are still going to add it. And that just looks like this. And then basically we're going to stop when the availability of ore is smaller than the amount needed. So if still needed count is bigger than 0 and let's see how we can do that. Okay, I'm not going to solve the end of today. I'm going to look at Alex's solution right here. Python. All right, so that is really small. Wow. Okay, so actually I wrote so much code. Let's see, and let's see if we can run it also. Day 14 input.txt, and we are gonna run it. And we get 2 outputs, and you're doing a binary search. Okay. So for 1, you're looking at how much ore is required, and you're looking at you're making a dictionary, and you say you want a certain amount, and you're using functions. So that means you can do like a recursion, I guess. Do you use a recursion? For the binary search, you do a recursion, and for the first part, you don't. So you're gonna do a loop. Actually, that's what I was doing. So you're taking the amount of fuel that you need. Basically, it's a bit similar to what I was doing. So you have a dictionary where you add 1 item by default, I suppose. Or is your default dictionary going to... How does that work? You have items, and in each item you have an element and an amount. Okay, so it's the same structure as I have. I just am not used to this notation, but I suppose that it means that you're just starting with a dictionary with these values by like initially. And so as long as the element isn't ore and you need more than 0, you're going to take those elements and you do next, which means it's the first item in the list, sort of. And that's because you're using a dictionary or maybe something else, and you're, yeah, instead of popping, you're just going over the next one. Okay. Then you take out the reaction and you see how often you have to run it, and you're using a ceiling as well. So the amount of reactions for the needed count, which is the last item in your reaction, and then the first element, which is the count of the production element. And then you're going to run the reaction multiple times. Oh no, you're going to actually take all the inputs for that reaction and run each of them. And you're appending what you need for those, and that is for each element. The second item, that is the element name that you need. And this is how many you need and how often is how much you're gonna run it. And then you're actually saying -1 if the required element is the element that you are looking for. How is that? So, oh, I think that's a part that I didn't realize. Is it possible? Is it possible that you are outputting an element and you need the element itself also to produce something? Like a kind of feedback loop where you're using one element as a catalyst and you're producing more of the same element. Since you're producing something, you want less of it. Ah, so yeah, okay, so you're subtracting right away from the produced element. So I was keeping track of the available elements and the needed elements separately, but I could have done it that way also, and maybe that would have made it a lot easier. I think that would have been a little bit easier. I've pasted here in a Scratch file. Yeah. Okay, yeah, that makes sense. So I think I got all the elements right. Well, I did solve part 1 correctly, just with a whole lot more administration than what was necessary. And then for the second part, you're doing a binary search. And let's see if you're searching from the ore or if you're searching from the fuel. So you're running with 1 and 1,000,000. Oh, what is 1 actually? Lower and upper. Okay. I'm not sure exactly how that works. So what you want to know how much ore is required for the midpoint. Ah, I see. So you're basically trying a certain amount and seeing if it works. Okay. So how much ore is required for a certain amount? Ah, okay, so you're starting always with the midpoint. Yeah, that's pretty cool. So I'll show on the whiteboard how that works. So you can, let's say, you have a certain range of possible amounts of fuel between 0 and like, let's say 1,000,000. I'm not sure what the number is. It's like a trillion maybe. And so you say basically, can I produce, or how much ore do I need to produce exactly half of that? So we have ore. And then you're probably going to check, do we have that amount of ore? And if it's smaller than what we have, then probably it's not working. So this one is wrong. And then you're going to, again, search between here and here. So then you're going to take this midpoint. And so you're keeping track every time of your lower bound and your upper bound. And that's it. So if you tested the midpoint, then either your lower bound is going to shift or your upper bound is going to shift. And you keep going until you find, yeah, the stopping condition is not clear yet. Let's have a look at that. So it is maybe easier than rewriting the whole function that we already made before. So the lower, if you actually cannot search anymore, that means that you are basically at a certain point. So let's say you went here, then here, then here, and now your lower and upper bound are like so small that you cannot search anymore, then that's basically your answer. And you're always taking the upper half if you can. Yeah, it has log and complexity, so the initial upper value doesn't really matter so much. Right, you can make it super big. Yeah. So if the number of OR that is required for the midpoint is bigger than what you have available, you're going to do again a binary search with the same lower bound, but you're going to go take the middle point as the upper bound, -1, so you don't include it. And otherwise, you're going to include the middle point in the upper bound. Yeah, so if you would have chosen to actually look at how much is required is exactly the same as what you have available, then you would have, let's see, what would you have done then? Would you have done a binary search like this? Maybe? I guess it's just a one difference, so that's what you could have done. Okay, cool. Thanks, Alex, again for sharing your solution with us. And it's interesting, you did it the same way as I did, but just with a whole lot less code. Good job. And I hope you didn't drop too much today on your ranking. What rank are you on right now? I'll look on the global leaderboard and actually show what it looks like. So you're on 29. Oh, you dropped a whole bunch. Yeah, usually you were hovering around 22 and now it's 29. So good luck on solving the rest and try to stay up, of course. Yeah. Does anyone else have a solution for today that we can look into? If not, maybe I can still try to solve it. So how was I actually solving it? I was hacking into my reaction and I was just trying to keep running the reaction forever and ever until I run out of ore. That's kind of what I want to do. So if the available ore is 0, then we need to stop. And we do subtract from the ore. This is no longer relevant. And we need to subtract available, and that is what we're doing already. We don't say that we're going to need ore. Maybe I do want to kind of keep track of needed ore here. Let's do check if we need ore or not. And let's say that if we need elements and we don't have ore anymore, then we're going to stop. If available. But it can be that we have one ore available, but all the reactions that we are going to run cannot use ore anymore. Because the reaction requires 10 ore and we have only like 1 ore. So we cannot run until we run out of ore. There are many reactions, of course, that require ore. So it's also not so clear if we can just say that if the reaction we're dealing with right now cannot use any ore, that we're just done. Maybe we can, because we now know that every needed reaction is actually essential. It's not just an optional one. So let's say that if the input element that we need is ore and we don't have it available, then we're just going to quit. So I am actually going to add it to the needed list. No, I'm not. So if the input element is ore and available ore is less, the needed count is less than what is available, then we're going to, let's just really throw an exception or something. Raise value error, no more ore, produced fuel is this, and that is going to be the available of fuel. All right, there we go. And let's run my file. Produced fuel 0, okay. Oh, we need this much ore and we don't have it apparently. The needed input count is smaller than the available ore. Okay. Well, it seems like that is not going to be possible to solve on time. So thank you everyone for coming on stream again, and nice to see that everyone is still coming every day. And I will solve the rest of the puzzle later and try to share my solution on the start of the next day. I'll try to be a little bit earlier so I have time to show it. And if anyone still has solutions, please keep them and share them with me on the stream before we're starting with day 15 tomorrow. Thanks for joining. Have a great time, have a great Christmas, and good luck on Advent of Code. Goodbye.